Let's take a look at the bending stresses and their effect on the end of a beam, where we know that the bending stress is My on I, and that it goes from 0 on the neutral axis linearly up to a maximum. And in the negative y direction, we know that it'll be in tension. And we also know that stress is force per unit area. So for a given cross-section of area here, this also represents force as stress times area along the beam. So we could also think of this as a force profile, where here we have compression along the top and we're in tension along the bottom. If we look at the effect of that, in essence we have a very large force acting across the top to the left, and this stress profile generates a large force in the bottom. And these two forces are trying to push the beam apart along this shear plane, like so. And here we can see if the beam were to fail, the shear plane would be the neutral axis right here. However, there could be other planes in here, let's say this arbitrary plane here, that we might be concerned with, in which case, above it, we have a certain amount of force top, and then below it, keep in mind that this portion of the forces, these two will cancel each other out. So we'll have a force in the bottom, and these forces will be less than the peak force we saw before, but it still is trying to push and pull this shear plane apart. Let's take a look at this plane here. You'll see that we have a very small amount of force left here, force top. All of these forces cancel those out, and we're left with a very small amount of force in the bottom. And as such, this shear plane is still a possible plane, but it has far less stress on it. So the maximum shear would occur on the neutral axis due to the fact that these forces would be the largest. And if we'd like to calculate this shear stress, it would be force per unit area, where this would be the force, and the area is the area of this plane along the beam down here. So this force is trying to shear the beam apart along that area. And the resulting equation will be tau will be VQ on IT, where V is the shear force, often found from a V and M diagram. I is the area moment of inertia. Of the cross section, which would be this portion over here. T is the thickness of the cut. And what I mean by cut is, if we're analyzing this beam, how wide is this cut going to be where the shear plane is being generated? So that would be T, and this we'll call X, this length here. So the cut is T. And lastly, Q is the first moment of the area beyond the cut. I'll talk about that in a minute. Let's take a look at the cross section of our beam, where this is the height of the beam, and this is the thickness, which we can call B, and the length of the beam goes back into the board like that. So we're looking at the end cross section. And since it's rectangular and symmetric, we know that our neutral axis will be right here at h on 2. And we can define I as 1/12 bh cubed. And what we mean by Q is the following. It's the sum of the A, I, Y bar, I. It's the first moment of the area beyond the cut. So if this is our cut here, T will equal B, and this would be the area beyond the cut. So the value for the area beyond the cut would be B times h on 2. And the centroid for the area beyond the cut would be right here in the middle at h on 4. So Q then, for the neutral axis, being the cut, would be the area 1/2 BH times the centroid 1/4 H, which will give us 1/8 BH. What if we were interested in this region above this line at h over 4? This would be the area beyond the cut. And at the cut, T would again be equal to B. And therefore, A would be 1/4 of H times B. And Y bar, the centroid, would be here, as measured from the neutral axis. And that would be 3/8 of H. So Q1, we'll call this, would be 1/4 HB times 3/8 H, which gives us 3/32 BH squared, which you can write over here. And you can see that Q is decreasing as we move further and further out. What if we were to even go higher up to here and look at this region? Well, here, this will be the area beyond the cut. And I think you can see that A is decreasing, which means that Q is decreasing. So as we move further and further away from the neutral axes, the area beyond the cut is decreasing, which lowers the value of Q. When we get to this outer edge, in fact, Q will go to 0 here. So Q will be a max when you're on the neutral axis, because you have the largest amount of area, and then we'll go to 0 when you reach the outermost fibers. And when we look at this equation over here, our horizontal shear stress equation, you'll see that these two values are constants. And Q and T represent the location of the cut. If we look again at the beam that's undergoing the bending moment, here's our cross-sectional area that we were just looking at. And here's our beam going back along here. And right here along the neutral axis is our shear plane, which we could show here. So that's the shear plane. And it has a thickness of T here at the cut. And let's call this distance X. And that's the area that these forces out here are acting across. So from here we can say that the shear stress is force per unit area, where it's this force over that area. But we know the shear stress is also VQ on IT, which would be force, and the area of the plane is T times X. We find that we can cancel through with these T's, and we get something called Q, the shear force flow. Has units of force per unit length. And what it represents is per unit length along here, X, how much force is acting on that specific surface as this thing is being pulled apart. And this is extremely useful. So this represents the force per unit length in this case X, along the beam. In summary, we have a horizontal shear equation as VQ on IT. We've defined Q as the first moment, which is A times Y bar of the respective parts. And we have the shear force flow Q as force per unit length, or VQ on I. Here we have a simple I-beam that was constructed from 3 1-inch by 2-inch wooden planks, and they've been glued together here and here. And we're asked to find the maximum V force that this beam can withstand without breaking the glue, which has a rated shear stress of 120 psi. Now the first place to start with all these problems is determine the value for Q, I, and T, and then we can figure out what V is going to be equal to. So the neutral axis is the centroid, which with symmetry we know is right here. And here's our cut. So that's T by definition, the thickness of the cut, which if these are all 1 inch by 2 inch, we know that T is 1 inch here. So we need to find I, and that's of the total cross section. It has nothing to do with the Q, and it's a constant. And there's a few ways to do that. One way would be to do it as the center portion plus the 2 wings, or we could do it as a large box minus the 2 smaller holes. I'll set up both so you can see how they work. For this one, we'd have 1/12 BH cubed plus 2 times the parallel axis theorem, so it'd be 1/12 BH cubed plus A offset distance squared. Or if we wanted to use this method, it would be 1/12 BH cubed for the large rectangle minus the small rectangle, and since they have the same geometry about the neutral axis, we can treat them as one square, in fact. So 1/12 B would be 1 inch. That's a half plus a half times the height of 2 cubed. which I believe this is easier to do as a subtraction rather than doing the full parallel axis theorem over here. So let me continue with this one. So it will be 1/12, where b is 2, and the height for a large rectangle would be 4 cubed minus 1/12 times a half plus a half, 1. And the height of those squares is 2 cubed, which gives us 10 inches to the 4th. Let's keep track of our data over here. We have I as 10 inches to the 4th. We define T as 1 inch, and that's our cut. And now we need to find Q. Now Q is the first moment beyond the cut. And what I mean by that is, here's our cut. That we want the Q of. The first moment of that area with respect to this axis. So in this case, there's only one piece. It'll be a y bar of that. And the area is 2 square inches. And the distance to its centroid is here as 1.5. And that'll give us 3 inches cubed for Q, which we can record over here. And we have a tau allowable of 120 psi. And with that, we have all of our data to solve this problem. If tau is VQ on IT, we want V out of that. So V will be tau IT over Q, 120 psi, 10 inches to the 4th, 1 inch cut, over 3 inches cubed. And if you check these units, pounds per inch squared, you'll see that this inches squared, we'll take away 2 of those, and we have inches cubed left, which cancels with this inches cubed, and we're left with only pounds here. 120 divided by 3 will be 40. So we get a V allowable of 400 pounds for the maximum shear that could be applied to this beam externally. What this tells us is if we exceed this 400 pounds of shear force, this glue joint here, or down here because of the symmetry of this, will break and the beam will fail in horizontal shear. This top panel will break loose from the bottom portion. Now what if we decide not to glue it, but rather to screw it together with some screws? So we'll place some screws inside of here. And we're told that the force that each screw can withstand is 200 pounds. And it's technically a shear force. And if we're going to solve anything that involves a force, we want to use this form of this shear flow. So our shear flow Q is VQ on I, where we know all these now. V is 400, Q is 3 inches cubed, and I is 10, which will give us 120 pounds per inch. So that's the force per unit inch, the force per inch along this beam going back into the board. So every inch going back, that little region right there has to carry this 120 pounds per inch. And since Q also is equal to the force per unit length along the beam, where X is the distance going back along L, we can solve for the spacing required for the screws to hold on to this shear force. So X will be F over Q, where F is 200 pounds per screw and Q is 120 pounds per inch. The pounds will go and we get 1.5 inches. So that tells us that we would need to place a screw every 1.5 inches going back along this beam, and the same for the bottom if that's what we decide to do as well. So this gives us the screw spacing. What if we chose 2 inches instead? Well, for 2 inches, we would need to hold 240 pounds, which these screws are not designed to do. So the shear force flow is useful. It tells us how much force we have per unit length along the beam holding something together. What if we decided to glue it like this instead? What if we use a 1x4 and we have 4 1 by 1/2 inch wings that we attach with our glue, let's say. Find V max. So in this case, here's our cut line, and that's T. And this is the region beyond the cut. So when we say beyond the cut, we're thinking from the neutral axis, what's beyond where we're going to cut it to analyze it. So that's our region beyond the cut. So solving this, we have T is still 1 inch. And Q now is AY bar of this region up here. So it's 1 by 1/2 times its centroid distance, which will be 1 1/2, which is 0.75 inches cubed. Notice how much less that is from the 3 that we had before. And as such, we can now say that tau, which is VQ on IT, we're solving it for V. So V2 here in this scenario would be tau IT on Q, which is 120, 10, 1 over 3/4, which will be an incredible 1,600 pounds. The reason this is so large compared to the 400 we had before is we're asking how much shear force does this cut need to carry. And that cut is only carrying that much area. It's the same for this cut if we analyze this one, by the way, and the same for this one and this one. In the earlier question, we asked how much V can this beam hold if that's our cut, and we're carrying a lot more area. That does not mean that this region is still not of concern. If we apply a V of 1,600, 4 times that, this region here, which we designed at 120, would actually have 480 psi required there. Now, if the wood is that strong and we're not gluing it or connecting it, then we could be okay. However, we would want to come back and check the limitations for the wood. And if we are concerned with the wood, we should check tau max, which will occur on the neutral axis. And the reason tau max always occurs on the neutral axis is that's where we get Q max, the largest possible value for Q. So if the wood is of concern, this region right here would be the region where it would fail in horizontal shear. Again, we have T as 1 inch in this region. And we need Q, which would be A, Y bar. And now we need Q of all of this area above. And there's a few ways to do that. We could do it as the AY bar of that region plus this region. We could do it as the AY bar of this region plus these two wings. Or we could do it as this large region minus these two smaller holes. And any of those will work. So we'll do this as a composite. And I'll pick large region plus small region. So we have 2 inches squared times the centroidal distance here, which is 1.5, plus this region right there, which is 1 inch squared times a half, which gives us 3.5 inches cubed, which we can see is larger than what we had before at that cut. Therefore, tau max on the neutral axis be VQ on IT, which is 400 pounds, times 3.5 inches cubed, divided by 10 inches to the fourth, and 1 inch cut. 140 psi, and we could check that with the values for wood. If this was Doug fir, the tau max is about 1100 psi. So we're well within our criteria here, so the wood is not going to be a problem. This glue joint is the problem right now, and that's a case where moving the glue joint out to here might be a better design. In that case, this would increase by 4-fold to 560, which would still be okay in terms of the wood failing on the central neutral axis. Thanks for watching.